Hello. In today's video we're going to be talking about Chapter 17, Lecture 17, Learning Objectives 3 and 4. We're going to look at complex ion formation and how it affects solubility, and we're going to look at our separation of cations and anions based on their solubility characteristics. So we're going to go back to looking at solubility of ionic compounds, so hopefully you guys remember it, although I do have a chart in here for you guys to look at and remember, hopefully. So let's start with the idea of a complex ion. A complex ion is just that, it's an ion that's complex. So it's going to be a substance that has a charge, so it has a charge. There are both cationic and anionic complex ions. And what it is kind of a Lewis acid-base theory with this. So we have a metal ion that is acting as a Lewis acid and a bunch of Lewis bases, so things with electron pairs that are acting as small Lewis bases. So we have a Lewis acid, which is a small, highly charged metal cation plus multiple Lewis bases, which are going to be electronegative atom containing covalent substances. And we have to have a lone pair of electrons. On these. So some examples of our acid. Include iron 3+, aluminum 3+, silver plus, copper 2+, several different things. Cobalt, cobalt 3+, many different things. Nickel 2+, and then some base examples include water, ammonia, cyanide ion, chloride ion, so things with electron pairs. So it's going to affect our solubility of our insoluble salts, and it's going to increase them. Because what happens is it takes those metal cations that have dissolved, whatever has dissolved, and it forms these complex ions, which then causes a shift due to the Chatelier's principle back towards more ions so that we can form more of these salts, or these complex ions. So the formation of these complex ions is very favorable. They get their own K value called Kf, and is very large. So we generally think that any ion that is in solution will form these complex ions. So it will basically, so if we start out with a concentration of silver ions, those will all convert into the complex ion if we have ammonia around, for instance. Because we have some examples of complex ions. something like that. So we've got lots of different ones. Okay, so let's look at how this actually affects solubility. Excuse me. Okay, so let's look at silver chloride. Silver chloride is considered an insoluble salt. So it's going to have a KSP associated with it, right? So AgCl, it's going to dissolve, produce Ag ions and silver ions. Okay. This has a KSP associated with it, right? That KSP is 1.8 times 10 to the negative 10, so it's not very soluble. Now, if we were to put this into ammonia, so this is impure water. In ammonia, our silver ions are going to attach to ammonia in solution, and this has a KF. So we're making a complex ion, so it has a KF associated with it, and it's 1.7 times 10 to the 7, so it has a very large KF. So any silver in solution is going to form our ammonia complex. Okay? And then, so we assume that all of them, it's basically a one-way arrows, that any of this that's in solution is going to form this. And overall, we get the following equilibrium process if we combine the two equations. Okay, so combining the two equations, we get this, and our K for this, which I'm just going to call Kc, is going to be the two values multiplied together. Which gives us a Kc value equal to 3.1 times 10 to the negative 3. So, any silver that's in solution is basically going to be this substance right here. And by making this K value so much larger than it initially was, we've increased the solubility of this complex. Okay, and we can see that relationship when we look at concentration of ammonia versus solubility of AgCl. In pure water, it starts out very, very low, and it increases exponentially as we increase our ammonia concentration. So with any of these complex ion problems, you want to go ahead and solve for this Kc value. And then once you have this Kc value, you can kind of use this as a what am I looking for? A equilibrium problem after that. So let's try. So we want to know how much Ag plus is in solution when concentrated ammonia is added to a silver nitrate solution if we have this. So we've got Ag plus in the form of silver nitrate, and we've put it into ammonia solution. So AgNO3 is a soluble salt, so it'll completely dissociate to produce silver ions and our nitrate ions. Right. And then we've got our formation of this complex ion. And we can assume that all of this forms. Because of this large Kf. Right, so all of our silver got converted into this complex ion. But we're looking at basically, is there any silver in solution? Because this is still an equilibrium process. So if we were to flip this equation, we can actually look and see how much silver is in solution. So if we take our complex ion and we look at its dissociation, into silver ions and ammonia ions, our Kc here is going to be 1 over 1.7 times 10 to the 7, which gives us a value of 5.9 times 10 to the negative 8. So not a lot going on here. But we're still going to do a Rice table with it to figure out how much silver we have in solution. So we assume that all of our silver got converted into the complex ion. So that 0.01 molar silver nitrate became 0.01 molar silver ions, which then became 0.01 molar of our silver ammonia complex ion. And we have a 0 here. And we started out with some concentration of ammonia, and after that we ended up at a concentration of 0.20 molar here. So it really doesn't matter what we start out with. Here at equilibrium we have 0.20 molar ammonia. Okay, so minus x plus x gives us 0.010 minus x, and 0.2. We can then put this into our K expression, where Kc is equal to Ag plus NH3 squared divided by our complex ion. So our Kc in this case, again, is 5.9 times 10 to the negative 8 equal to x times by 0.20 divided by 0.010 minus x. This x is a small x, so we're going to get rid of it and set it up as 5.9 times 10 to the negative 8 is equal to 0 squared times by x over 0.010. Okay, and then when we multiply this out, we get an x value equal to 1.5 times 10 to the negative 8 molar. And that x is our silver ion concentration. So we see basically all of it has converted into silver. So anytime you approach one of these problems, you make the assumption that all the ion in solution forms a complex ion because the Kf is so large. After you've made that assumption that all of it is converted there, then you can look at how it actually dissociates. So all of it has formed our silver complex ion, and then further from there has dissociated. Okay, let's look at a little bit more about solubility. So we have something called amphoterism, where a metal oxide or a metal hydroxide is highly soluble in a basic solution or highly soluble in an acidic solution, but has very low solubility in pure water. So these are metal oxides and metal hydroxides. That are highly soluble in highly basic or highly acidic solutions, but have low solubility in pure water. Okay, so what happens is if you have the oxide and hydroxide, you consider it to have a basic salt. So it has a basic anion. And that basic anion will react with the H plus to produce water. That will cause us to have greater solubility. So it's basically taking away our anion, which causes a shift towards our ions. So you see that right here. We have aluminum hydroxide. When it reacts with H plus, that H plus produces water with the hydroxide and aluminum 3 plus ions. Another thing that happens with a lot of the metal oxides and metal hydroxides is we'll form, if we have a large amount of hydroxide, we'll actually form a complex ion. So either our hydroxide or oxide will react with hydrogen to produce water, or the hydroxide will react with our complex ion, or sorry, ion to react with our insoluble compound to produce a complex ion. So, in regular water, insoluble, in acid produces water and ions, in base produces complex ions. Okay, last thing I want to talk about is selective ion precipitation. So, if you want to take a solution that contains more than one ion and you want to form one of the ions to remove it, or form a salt in order to remove one of the ions, and then follow through and remove the second one. So what we do to selectively precipitate an ion is we look at solubility of the salts they form. So if we have something that has a lower KSP, it has a lower salt solubility, so we can use that to our advantage. So for instance, if we have two ions in solution, we can add in a salt that will selectively precipitate one ion over the other. So you just look at the one that has the lower KSP. For instance, we have on the left, we have a solution containing zinc 2 plus ions and copper 2 plus ions. And what we can look at is a sulfur compound, or a sulfur salt. So copper sulfide has a KSP of 6.0 times 10 to the negative 37, while zinc sulfide has a KSP of 2.0 times 10 to the negative 25. So the KSP of zinc sulfide is significantly lower than the KSP of copper sulfide, so we can take and add in to our solution H2S, and that will cause a precipitation of copper sulfide. And it's because our copper sulfide, just going to put this up here, Cu sulfide has a KSP equal to 6.0 times 10 to the negative 37. So it will precipitate out before zinc sulfide, which has a KSP equal to 2.0 times 10 to the negative 25. So you can see this visually here. The copper ions in solution have a blue color, and as you add in the H2S, that color goes away and you get that precipitate down at the bottom. That precipitate can then be filtered out, and what you're left with is zinc 2 plus ions. Okay? which still has the ability to react with the sulfur. However, we haven't reached its solubility limit yet, so in order to get the reaction to shift in the direction we want, we need to do an additional thing. If we look at this reaction, hopefully we notice that we have H+ ions. So what we can do is we can add in OH-, and that will cause water to form, and it will shift in that direction because we're removing a product, so we're going to shift towards products, which will cause the precipitation of this species. So if we increase our pH, we'll then get a precipitate of our zinc sulfide, which can then again be filtered out and removed. So let's try using information about solubility to try and separate the following two. So we have copper hydroxide, or copper 3 hydroxide and iron 3 hydroxide together. And then we also have a solution of Mg2+ and K+ together. So copper hydroxide, iron hydroxide, these are probably going to be two insoluble salts. They have very low solubility. If we look at this table right here is a solubility table. We look at our chromium, it's not on here, but all hydroxides generally are going to be insoluble with very few exceptions, and iron and chromium are not exceptions to that. So these are going to be things, here we go, here's iron 3+. Iron 3+ and chromium 3+ are going to be insoluble in hydroxides. So we have probably this slurry mixture where we've got a bunch of solid in there, and we want to be able to separate out these two substances. So we look, if we have two solids, we're going to have to make one of them more soluble. So we're going to look over here at our formation constants. And we see on here that we can form this species right here. So we have a hydroxide-based chromium complex ion, but we do not have an iron-based hydroxide, or a hydroxide-based iron complex ion. So what we can do is we can increase our hydroxide concentration, and in doing that, since we have such a very, very large Kf for that, we can cause chromium hydroxide to become soluble. And once we do that, we can add in, or we can filter out, the iron hydroxide. And then we could decrease our pH again. So I'm going to take CrOH plus OH minus to produce this species to increase our solubility. Then we can go through, we can filter out the iron hydroxide, and then add H+ to neutralize and reprecipitate. Okay, so that's how we can go about separating chromium hydroxide and iron hydroxide. What about magnesium 2+ and K+? Here we're going to have to find a problem or a salt that we can add in that will make one of them insoluble. So the first one, we had to make one soluble because they're both insoluble salts. Now we have two soluble ions, and we need to figure out how to make one of them insoluble. And if we look at magnesium versus potassium, they're right next to each other, we have several options we can choose from. Probably the easiest is to add in hydroxide. So if we take our magnesium 2+, do some erasing. If we take our magnesium 2+ and we add in hydroxide ions, we'll produce insoluble magnesium hydroxide. So we can go through and actually make our solution more basic, and then we'll precipitate that out. We can filter it out, then we can neutralize and basically just dry it to get rid of the potassium. Okay, that is everything for this video and this lecture and chapter 17, and for the test. Yay! So, see you guys later.